Okay, so today we're looking at nuclear fusion and nuclear fission. Now, fusion is the bringing together of two things, fission is the splitting apart. So we're going to look at nuclear fusion today, which is the joining together of two nuclei. And we're also going to look at the splitting of a single nucleus, which is called nuclear fission. Now, it's really a bit exciting today because what we're going to be looking at is the famous equation E equals mc squared, which is Einstein's famous formula, where E is energy, m is mass, and c is the speed of light. And this helps us to understand the energy that can be released when we have fission and fusion reactions. Now, the thing about E equals mc squared, it's very famous, of course, it's on a lot of things, but also the fact that it was directly responsible for the creation of atomic weapons. Now, it wasn't something that Einstein foresaw, and in fact, Einstein is very much against war, and he was quite dismayed at how this equation ended up being used. But essentially, he became aware that Germany was looking at the possibility of using this kind of information to build an atomic weapon, and he wrote a letter to the President of the US at the time, Franklin Roosevelt, urging him that really, maybe get on it because stuff's happening in Germany. And essentially, his equation and that information led to the United States developing the atomic bomb in what's called the Manhattan Project. So you may have heard of that. If you're a fan of Watchmen, you might know that one of the characters, Dr. Manhattan, is, radioactive because he's to do with the Manhattan Project. That's why he's named. And so it led to the creation of the atomic bomb and, of course, the huge loss of life when those bombs were dropped in Japan, and particularly in Hiroshima and Nagasaki. So he was really disgusted and sad and upset by what happened with his finding, E equals mc squared. But it's really important for us to understand today how this equation is used and really all the power that comes from simply splitting and fusing nuclei of elements. The huge power that comes from that, it's pretty spectacular and pretty terrifying at the same time. So last lesson we looked at the binding curve for elements, and remember this was the energy required to split an atom, a nucleus, and we saw that iron has a really high binding energy because it's quite hard to split, it's very stable. But today we're going to have a lot of focus on uranium. So first thing we're going to look at is nuclear fission. Nuclear fission was first investigated in the 30s by Enrico Fermi, who was firing neutrons at uranium, and he found that the products that split off actually had different half-lives to the uranium he started with, so he's very excited. He thought he'd discovered some new elements, but what had actually happened is his uranium that he was firing neutrons at had split into fission fragments. And depending on how you do this experiment, you can end up with different fission fragments, and he had things like bromine and antimony and cesium and other things. So it's this idea of firing a neutron into a nucleus and splitting off into new elements, as well as often other particles such as other neutrons that can happen. And that's what we can see here in these possible equations for fission. There's lots of different ways fission can occur depending on the conditions. So this top one is one we're going to be focusing on a bit in the next section. And so you can see here you've got uranium plus a neutron goes to uranium again, but this is a isotope. Can you see 236 versus 235? And this is an unstable isotope. It splits, and it splits apart into two different elements, La and Br. As you can see on the next table are lanthanum and bromine. And also three neutrons, so some other particles, plus energy. Okay, and there are other ways that uranium can split too. Now underneath here we've got the table that actually links to this circled equation. So both of these are all in your textbook. You can see here this is kinetic energy and binding energy. And what happens with the nuclear fission reactions is you have kinetic energy, which is the difference between the binding energies of your products and your starting material. So if you can see here the binding energy of uranium and the binding energies of our two other elements, which are lanthanum and bromine. And they're in fact in this table. It's a table that I've printed out and given to you. We're going to use these binding energies to try and find the energy released in fission and fusion reactions. Now, you can see they're all different. You can see here that, for example, uranium has a higher binding energy. It's more stable than the products that spring out from it. But in order for this equation to essentially balance, you can see here that you've got these two together elements have more energy than what you started with. So to account for that, we actually have a loss of energy through kinetic energy. And that kinetic energy is in the neurons, okay, that we have coming out of the fission reaction, so in these guys here. And you can see here the distance, that is the difference. See, there's a little bit more than the uranium had in binding energy. That's actually the amount of kinetic energy. And this is the kinetic energy. This energy here that's released is the energy that is going to be causing all of the problems when we're looking at fission and fusion reactions. So we're going to be using this table to help us calculate this difference, this kinetic energy, which is output in fission and fusion reactions. So the whole idea is that the products and the original starting material have different binding energies, and we look at the difference. And once we take away some of that energy and kinetic energy in motion from these fragments flying apart, you then end up with total energy being the same. So we have a balance. Energy at the start is equal to energy at the end, but we lost some in kinetic energy.